Now that we have an understanding of planes, we're going to look at some of the geometric properties of planes and questions that are geometric in nature that are asked about planes. And probably some of the most basic of all geometric problems involve the question, are two planes parallel, or are two planes perpendicular, or neither, right? So let's start with the idea of having parallel planes. And I'll make it really obvious by essentially just drawing them like this. So here is one plane. And literally, if I just take that plane and let's say I copy it and I paste it below here. Let's say I just move it. So I literally have a copy of these two planes. And now let's say I were to draw the normal vector. So I could, again, remember I can draw the normal vector with any initial point in the plane. So let's say I pick this point and I draw that. Let me just call that N1. And then if I do the same for the second plane, let's say I use this point and I make that one a little bit longer. Let's say that's N2. Well, what is true is this. Plane 1 and plane 2 are parallel if and only if their normal vectors are parallel, right? So that's the basic fact. So two planes, and let me say it like this, two distinct planes, meaning they don't pass through the same set of points. They're not identical. It's not like I copied this plane and then put it right on top of it. No, I made sure that there was some, in this case, vertical distance between them. So two distinct planes are parallel, right? If and only if their direction vectors are parallel. So if their direction vectors are parallel. Now, so what do we know about vectors that are parallel? Well, two vectors are parallel. There are different ways we can, I'll say it in two ways. If one is a scalar multiple of the other, so if normal vector 1 is equal to some constant times normal vector 2, right? Also, remember, we can use the cross product to determine if two vectors are parallel. So two vectors are parallel if and only if their cross product is equal to 0, right? So we could do this. So this is another thing we could do. Now, obviously, computing the cross product is a little bit more involved than checking to see if two vectors are scalar multiples, but it works, right? So you could take n1 crossed with n2, and if that cross product comes out to be the zero vector, then you can conclude that the two vectors are indeed parallel, right? So there you go. And so that's these are two relatively easy things to check to see if two planes are parallel. Now the key is to be able to identify the correct normal vectors. And when we get to a couple examples, you'll see how, again, even that process isn't very difficult at all. Now, what would it take for two planes to be parallel? Okay, again, I'm going to make this really obvious. So I'm going to draw something that kind of looks like what we would draw for an XY plane. And then I'm going to draw something that looks like the XZ plane. So basically here, like that, so we have this, right? So here are two planes that clearly are at 90 degrees to each other. So again, let's do the same thing. Let's draw a couple normal vectors, because everything that we need to know about planes uh, pretty much everything will be determined by the normal vectors. So let's draw. Here is a normal vector for that plane. So we got our 90 degrees. There's our N1. And let's draw a normal vector for our floor, essentially. And it goes up like, oh, that's a little too much. But let's say there. And then that's N2. And look at what has to happen. Look at what has to happen for there to be a 90-degree angle between the planes, right? There would have to be a 90-degree angle between the normal vectors. So again, everything comes down to what happens to N1 and N2. So two planes. So two planes. I guess we could say, yeah, we could keep it consistent and say distinct. So two distinct planes are perpendicular if and only if their direction vectors are perpendicular or orthogonal or normal, all those words. Now, how do we determine if two vectors are orthogonal or perpendicular? The easiest way is to check the dot product. So basically, this scenario that I have graphed here or illustrated here on the left can only happen, right, when the dot product between N1 and N2 is equal to 0, right? So orthogonal, parallel. Remember that's again a distinction between the cross and the dot products. All right. So we see what has to happen for two planes to be parallel and perpendicular. Now the fact that the angle between the planes ends up being the same as the angle between the vector, that can be that this concept here can be now generalized and say, okay, if I want to find the angle between two planes, and let's say it's not an obvious 90 degrees, even though sometimes the 90 degree is not obvious when you're working with the equation, but let's say there's another angle here. So for instance, let's say I kind of tilt. So if I take this plane, right, which is again kind of looks like our XZ plane, but if I take it, so I'm going to keep this one basically like my floor, and let's say my wall for whatever reason now becomes tilted. So here, and then let's say here. So that 90-degree angle is now technically, let me draw. So this angle here is, I'm going to call that theta. Technically, if I were to extend, let's say my floor further this way, I would have another angle here, right? But just as how we essentially define the angle between two vectors as that smallest amount that you have to rotate one to coincide with the other, same thing here, right? That will be the smallest angle that we have to rotate this plane to get it to coincide with the other plane. Like you're going to step on it. So you either step on it and crush this plane into the other plane, or you open it up all the way back and have it coincide over here. We would go for the smaller of those two angles. So this is what we would define as our theta. But again, think of what would happen with the normal vector. So the normal vector for the red would still be here. But then now the normal vector for the blue, it would be, if let's say I drew it right here, then it would be pointing pretty much down this way. Let me change it to blue, kind of like that. So there's a 90-degree angle between the blue vector and yeah, that plane right there. It turns out that so if I now do this and extend, there we go, my red vector back here. So now I would define this angle as the angle between the two vectors, and then that would be, you can use a little geometry to confirm, in fact, that it will end up being the same angle here. But I wanted to start with the 90 degrees to show how clear that this is. It's just a little bit messy when you start having the one of the planes like tilted in a direction so that you don't have a 90 degree there, right? So what we want to do is, again, to make sure that the angle that we come up with is acute, right? So this is what we're going to do. So so these two planes, they intersect, and they intersect and form a line, but along that line, it's not a 90-degree angle, it's some other angle. So we define the angle. And this equation that I'm about to write down, which is something that we've used before, this works whether it's an acute angle or 90 degrees, right? It works either way, right? So we define the angle between two planes right? So between two planes as the acute angle between their normal vectors. So as the acute angle between their normal vectors. And again, we're going to use the same notation. Let me label it over here so it's clear. N1 and N2, right? So again, it comes back down to doing something with vectors. How do we compute the angle between two vectors? Well, we really just have one equation, and I'll write it down in just saying that the cosine of the theta that we have there. And remember, what we do is we have to take the dot product of the two vectors, so n1, n2, and then divide it by the magnitude of both vector, the product of the two vectors. So the magnitude of n1 times the magnitude, let me do this, times the magnitude of n2. Now, remember that if the dot product happens to be a negative number, it is going to give us that obtuse angle. We want again, in the definition, the acute angle. So I have to ensure that there's something positive in the numerator. I know that there's going to be something positive in the denominator because both magnitudes are going to be positive. The product of two positive things is positive. But what could I do to guarantee that the numerator is always positive? We take the absolute value, right? So to ensure that we get the acute angle, which is what we want, that smallest rotation, right? We take the absolute value of the dot product of the two vectors, all right? So yeah, so there you go. You have concept of parallel, perpendicular, and if it's neither, right? So if the planes do intersect at some angle other than 90 degrees, we can use this formula to compute it, right? Okay, let's do a couple examples, and again all these questions that we're going to work on are geometric in nature, right? So let's see what we can do. So let's look at question 1. So are the planes, let's write this down, 3x minus 4y plus, my plus sign's a little close there, so plus 5z equals 0. And the other plane is negative 6x plus 8y minus 10z is equal to 4. So are these planes identical? Meaning, are they the same but just written in a different form? So are they identical? Are they parallel? Are they perpendicular? Right, so we'll answer those, and what is the angle between them, right? So if, for instance, they are the exact same plane, then technically the angle between them would be 0, right? So we'll see. So what is the angle between them, right? So kind of a good question where we essentially get to try out all the little techniques that we just talked about. So let's see identical. Well, how could we determine if they're identical? So let's start with the first equation. We have 3x minus 4y plus 5z is equal to 0. So this, when you look at this, it's written in the, not the point normal form, but like the standard form where you have all your variables on one side, have your constant over here. This one is kind of written in that form as well. But if you look closely, it seems as if the coefficients of this plane, so let's write it beside it, the negative 6x plus 8y minus 10z is equal to 4. Notice all these coefficients are multiples of 2. So let's go ahead and let's actually divide by negative 2. So if we divide all 4 terms by negative 2, then this left-hand side becomes 3x minus 4y plus 5z. But then on this side, I'll end up having a negative 2. Now we can see that these two planes are actually, they're not identical, right? So they're not identical. So let's say that. Why are they not? Well, on this side, on the left-hand side of both equations, the expressions, the expression is the same, but they're not equal to the same constant, right? So the planes are not identical because their equations are not identical. So their equations are not identical. Okay, so the question is, are they parallel? Well, when you see it, so now as far as identifying if they're parallel, so if I call them, so now right beside it, I'm going to write down the normal vector. And the way you can identify the normal vector just by looking at the equation in this form, the normal vector n will have components that are the coefficients of the respective variables. So n1 in this case is the vector with components 3, negative 4, 5. And then this plane will have a normal vector that's not even just a scalar multiple, but it's exactly the same, right? The exact same thing. So since n1 is equal to 1 times n2, I mean, you can say that this is your scalar. The normal vectors are parallel. In fact, they're actually equivalent, but I'll just say parallel. The normal vectors are parallel. So the planes, put a comma there, the planes are parallel. So what does that mean? Well, it's not quite the, where I had them kind of flat, like the XY plane, and then I just kind of moved it up. But basically, it's more something like this, something like that. And I'll do my same old copy and paste trick, and then just kind of move, in this case, move it up. And yeah, there you go. So they are parallel. And because they are parallel, they don't intersect, and there is no angle between them, right? So since the planes do not intersect, and that's because they're not the same, they're not identical, but they are parallel. So since the planes do not intersect, the angle between them is undefined, or you could say does not exist. So the angle between them does not exist. There you go. All right. So nice little question, not too difficult, but and again, it utilizes what we talked about. So let's look at a final example and say this. So let's look at an example that involves a line, which we've studied quite a bit, and now planes. So does the line, and let me fix this. So I'll go ahead and write, so does the line, let me write it in our standard form, vector form. And here is the line 3 plus 8t, comma, 4 plus 5t, comma, negative 3 minus t. So does this line intersect this plane? X minus 3y plus 5z is equal to 12, right? So, what does that look like? Well, so we have a plane, whatever, the plane looks like, and we have a line. So, and again, you could draw something like the normal line, but it doesn't have to intersect it at 90 degrees. It could be a line that, kind of does this. Maybe it, passes through that particular point, right? As opposed to a line that might be like this, right? So you might have a line that's kind of that's parallel to the plane, and therefore they never exist, right? Or you could have a line that passes through just a single point, or you technically could have a line that is entirely in the plane, right? So these are just some examples of what could possibly happen when you're looking at a line, um, possibly intersecting with a plane. It might never happen, right? It could happen at just one point, right? I know this one looks like it touches at a lot of different points, um, but no, it's just at that point, as opposed to something like this where it lies in the plane, right? Okay, so let's see how we could answer this question. Well, if you think about it, um, the parametric form, so the parametric form of r of t is, so let's write the three components separately. So it's x equals 3 plus 8t, y equals 4 plus 5t, and z equals negative 3 minus t. Think about it. If it's supposed to intersect, whether it's the green or the red, there would have to be at least one value of t such that when I plug that value of t into um, the the equations for x, y, and z, then I would get a point that lies in the plane. So in other words, I would have to be able to find that the line and the plane, they have at least one point in common. So that means the equations of the line, these parametric equations of the line, would have to satisfy the standard equation of the plane. So what do? It means I'm going to take, so to kind of figure out the point of intersection, I'm going to take the x equation and I'm going to put it right there. Then I'm going to take the y equation. I'm going to put it right there. And then I'm going to take the z equation and put it right there. And what that will do, that will give me a linear equation for t. And if I get no solution, then it's the blue. If I get one solution, then it's the red. If I get infinitely many solutions, then that's the green, right? So you might remember when you studied the possible solutions for a linear equation, right? A simple linear equation, it's either no solution, one solution, or infinitely many. That concept is so helpful, right? So let's say this. So if R intersects the plane, right? So whatever defines the line, it would have to satisfy whatever defines the plane. So it's not quite, like when you study points of intersections of like curves, where you say, oh, you set them equal to each other. That in a sense, I mean, it's a helpful thing to say because it's easy to remember, but it's limiting because when you start getting into objects like this, where what does it mean to set like this equation equal to that equation? That doesn't quite make any sense. The more precise and more general concept is that whatever equations are used to define one object, they have to satisfy the equation of the other object. So if you take the x, y, and z of the line, then it has to satisfy the x, y, and z of the plane. So set this equal to 12, and there's our equation. So let's see, what do we get as far as a solution for t? So we have 3 plus 8t minus 12 minus 15t minus 15 minus 5t is equal to 12. So let's go ahead and simplify. So we have, this looks like, so 8 minus 15 minus 5, so that's negative 12t. And then let's look at our constants now. So 3 minus 12, that's negative 9, minus 15, so that's negative 24. Add 24 to both sides, and we get a 36. And there we go. So this implies that t is equal to negative 3. So yes, the line does intersect the plane. And this alone would be sufficient to answer the question, but let me do a little bit more. Suppose we wanted to know, so now that we know it's the red situation, right? So let's write that down and say, so yes, R intersects the plane at one point. But you can't say at t equals -3. So this intersects the plane at one point. Well, what is that point? Now that we know the value of t that forces the line to coincide with the plane, I can use that value of t back in my parametric equations to figure out what the x coordinate is, what the y coordinate is, what the z coordinate is. So the point of intersection, so the actual point that I have here highlighted in, or that red circle, so the point of intersection is x equals, so yeah, just take our -3, plug it back in. What do we get? So we have 3 minus 24, so that's -21. Y is 4 minus 15, so that's -11. And z is equal to -3 minus -3, and that's equal to 0. And this is kind of interesting as well. So here is the point. So I switched my digits, so -21, -11, and 0. So not only can we say that this is the point of intersection, but this is actually a point in the xy plane, right? Because z is 0, right? So this point, let's just say in the xy plane. Yeah, pretty interesting question here. Setting up the correct equation, obviously working through the mechanics of getting our value of t and making sure that how we interpret this. This is, you can almost think of this as when the line intersects the plane, and then this is where the intersection occurs, right? So when and where. Now, yes, the fact that the value of t is negative is not really a problem. You can think of this as like, suppose your reference point is t equals 0. Well, it would be 3 units of time before that reference. That's all that negative would mean. It's not suddenly, oh, you have negative time. It's just prior to your reference point. That's how the negative could be interpreted in this context if you interpret t as time. Otherwise, it's just some variable, and that variable allowed us to find our point of intersection. So some nice, I would say relatively simple geometric questions that involve lines and planes, and many of them come down to, again, working with vectors or vector equations of lines and so forth, right? See you in the next video.